And today we are going to discuss about the common emitter RC coupled amplifier, or simply an RC coupled amplifier. And this is the diagram of the RC coupled amplifier. In the last class we have discussed about the biasing, and we have seen the voltage divider biasing. So, the voltage divider biasing is used in the case of an RC coupled amplifier. So, this is the voltage divider circuit, and this is for biasing. R1, R2 is a voltage divider, and it is for biasing, and this RC is the load, and RE is for stability, and C is for to remove the negative feedback introduced by the RE, that is RE is required, but it will provide some negative feedback for both AC and DC signals. So, RE will provide a negative feedback. Actually, it is required for DC signals, negative feedback, that is, that change is very small, that is because of that beta change there can be that IC change will be there. So, that change has to be reduced due to change in the beta, but there should be a change, AC current change will be there, but AC, for AC RE should not give a negative feedback. So, that AC signal has to go through C, or C will provide a negative feedback, C will reduce the negative feedback due to the RE, or C is known as a emitter bypass capacitor. It is a bypass capacitor. Bypass means bypass, you might have seen Thrissur bypass, Calicut bypass, Ernakulam bypass, etc. Similarly, the AC signal has to pass through this C. RE will provide a negative feedback for both AC as well as DC, but for AC it should not give a negative feedback. So, that AC has to bypass through this, that is why we are giving this C. If we are not giving the C here, the gain of the amplifier will be reduced. Even without C it will work. So, these are the components. These four components are the components of a voltage divider bias, that we have seen. We have seen fixed bias, collector to base bias, and voltage divider bias in the last class. So, in addition to that biasing, we are providing some capacitors here. This is the output coupling capacitor. Coupling means connecting capacitor. That is a connecting, and here this is the input coupling capacitor. So, this R and C will effectively name this circuit as, this RC and C out will effectively name the circuit as the RC coupled amplifier. By using this is a coupling. In addition to RC coupling, other coupling is there, transformer coupling is there, and inductive coupling is there. Different types of amplifiers are there. We are using different methods will be, and again direct coupling is there. Instead of this C out, we can directly couple. We can couple directly to the input of another amplifier. So, this after this stage there can be one more stage also. So, if you are connecting that amplifiers one after another, it is known as cascading of amplifier, cascading. But here we are studying about only one stage. This is a single stage RC coupled amplifier. So, an RC coupled amplifier is a part of a multi-stage amplifier. Multi-stage means after this stage we can have another stage, wherein different stages of the amplifiers are connected using a combination of resistor and capacitor. That is, different stages are connected using a combination of resistor and capacitor. Then the next is the capacitor C in and C out are the coupling capacitors. Just in the diagram, C in and C out are the coupling capacitors, and their function is to block DC voltage and allow only AC voltage to the transistor. So, the function of this coupling capacitor is to pass only AC into here, and from here DC will be blocked. Otherwise, the biasing will get affected. If you are using direct coupling here, biasing will get affected. So, in the case of DC coupling or direct coupling, we will use circuits in such a way that even with the direct coupling it will not affect the biasing. Such circuits are there for DC amplifiers. DC amplifiers are also there. Normally almost all amplifiers are AC amplifiers, but some instrumentation amplifiers are DC amplifier. Instrumentation amplifier means some temperature change that we have seen in instrumentation systems. So, in that case these amplifiers are DC amplifiers. A temperature cannot change suddenly, pressure cannot change suddenly. So, these things speed cannot change suddenly. So, in that case we have to use the DC amplifier. So, a sudden change, but a voice signal will have a higher frequency compared to a temperature change. So, in that case we can use an RC coupled amplifier. So, the function of C in and C out are it is functioning as coupling capacitors, and their function is to block DC voltage and allow only AC voltage into the transistor. That is, it will block the DC and only it will pass AC signals to in and out. If any external DC voltage reaches the base of the transistor, it will alter the biasing conditions that I have told. If another DC voltage comes, it will affect the DC biasing condition. DC biasing means the transistor may come out of the active region and it will not function as an amplifier. And again, R1 and R2 are resistors and are called potential divider resistors or voltage divider resistors, that I have told you. R1 and R2 will provide the biasing, which bias the transistor in the active region. It will bias the transistor in the active region. Potential divider biasing is used here to provide high stabilization of the operating point. So, operating point means a fixed IC and VC point. IC and VC has to be same throughout the operation of the transistor. That is known as the operating point stabilization. So, in the other biasing, that is in the fixed bias as well as collector to base bias, there can be change in the operating point. And RC is the collector resistance which converts RC is the collector resistance which converts the collector current into the corresponding voltage. RC is actually the load. RC is known as the load. So, here this is the RC. RC is the load. RC is the collector resistance which converts the collector current into the corresponding voltage. RE is the emitter bypass resistor. RE is a bypass resistor, that I have told you. This is RE is a bypass resistor. Its main aim is to avoid thermal runaway. Thermal runaway means if there is no RE, there can be transistor may get damaged. That is, there is a term called as thermal runaway. Thermal runaway means when there is a if there is no RE, if due to beta change, if due to beta change there can be change in the IC may increase. So, when IC increases, there will be an increase in the temperature of the transistor. When current increases, normally temperature increases. So, when temperature increases, when again IC increases and again temperature increases, this will happen within a fraction of a second and the transistor will get burned off. That is, a smoke will come. That is actually known as a thermal runaway. And emitter capacitor C and emitter resistor RE makes negative feedback for making the circuit operation and more stable. That is, RE will provide negative feedback and C will remove the negative feedback for the AC. Actually, RE will provide the negative feedback for both AC as well as DC, but actually we do not want negative feedback for AC. So, we are bypassing that AC through CE. So, that is the functioning of RE and CE. And the next thing is the frequency response of an amplifier. Frequency response means the amplifier that we know that the amplifier has got an input, that is, we are giving the input here, we are giving an input here. So, we are giving a signal and signal will have a frequency from any value from low hertz to high hertz, high frequency, low value, low cycles per second to high cycles per second, or low hertz to high frequency. So, we are giving this value here, and the transistor, this amplifier may not provide the same amplification for all the frequency. This transistor may not provide the same amplification for all the frequency. Its gain will reduces with variation in frequency. Its gain will reduces with variation in frequency. So, we can see how the gain will reduces with frequency. That is, in the mid band, in the mid frequency region, the gain will be higher, and in the high frequency as well as the low frequency, the gain reduces. So, there are reasons for reduction of gain at high frequency as well as gain for reduction of gain in the low frequency. So, in the low frequency region, here you can see two capacitors are there. One is the coupling capacitor and bypass capacitor is there. So, coupling capacitor and bypass capacitor will provide high reactance at low frequency, that is, its effect will be it will provide a high reactance, that is, the signal will get attenuated here, and here high reactance means the AC will not pass through here, So, that means that AC will has pass through here. So, the negative feedback will be higher at low frequency, and negative feedback will be higher at low frequency, and again there will be more attenuation due to the high reactance. So, because of both of these, the gain reduction will be there at low frequency, that is, the curve will have a slope, and that will be 20 dB per decade, and here there will be in the high frequency there will be again gain reduction, that is due to the transistor internal capacitance, that is due to Miller capacitance, it is known as Miller capacitance, that is because of that Miller capacitance there will be reduction in gain at high frequency, that you cannot see that capacitor, you will study later while studying transistor in detail about Miller capacitor. So, there will be reduction in gain at high frequency, and there will be reduction in gain at low frequency. So, there will be a slope, and there is a in the mid band there will be maximum gain, and there is a point known as half power point. Half power point means it will be there in the lower slope as well as higher slope. In the lower slope it is here, and this point is known as half power point, that is, the power at this point will be half that of the maximum power, and that point is actually the maximum voltage divided by root 2, that is known as, that point is known as half power point, and this also in the high frequency cutoff also, high frequency roll down also there will be half power points. So, this half power point here is known as high frequency cutoff, and this point is known as the low frequency cutoff, and this value is known as the difference between high frequency cutoff and low frequency cutoff is known as the bandwidth of the amplifier, and ideally an amplifier should have infinite bandwidth. Infinite bandwidth means there should not be any low frequency cutoff, and there should not be any high frequency cutoff, but practically this is the response. So, this is known as the frequency response of the amplifier, that is, practically there will be a high frequency cutoff as well as a low frequency cutoff. So, because of this there will be a term known as bandwidth. So, again we can see there is a this is known as the bandwidth FH minus FL, and there is a term called as figure of merit of the amplifier, that is the bandwidth in gain. If this is high, if the bandwidth is high, gain, and if the bandwidth and gain is higher, means the figure of merit is higher. That is, this is a quality factor of the amplifier. If the figure of merit is higher, means the amplifier is good. And again we can see how an amplifier functions, that we have in the scene. So, normally this is the input signal that is given to the amplifier. This is the input signal VI, that is here we are giving the V input here, and we are getting an out of phase signal, that is totally out of phase. When the input is going high, the output is going low. So, normally it will provide amplification also. It is, if the VA is in millivolts, the V out will be in terms of volts, but the frequency is same, but it will be out of phase. We can see why it is becoming out of phase, that is the V0 is equal to, that is V0 here, the V0, this is the V0 is equal to VCC minus ICRC, VCC minus, this is the VCC minus ICRC. So, IC, when IB increases, IC increases, when input voltage increases, IB increases, IC increases, when that is IC is equal to beta times IB, IC is equal to beta times IB. When when input voltage increases, IB increases, so IC increases by beta times. So, there will be a voltage drop across RC will be higher, voltage drop across RC will be higher. So, in effect this voltage will reduces, this voltage will go down. So, the voltage across this increases, that means this voltage will reduces. So, that is why there is a 180-degree phase shift between the output and input. That is, here you can see there is a 180-degree phase shift between the input and output. So, that is the functioning of the amplifier. Actually, we can see how it is functioning. When the input voltage, if we are giving a sinusoidal voltage input here, like this, we are giving a sinusoidal voltage input here, sine wave. In the positive half cycle, IB increases, IB increases means IC increases. So, IC increases means this this current, IC increases means the voltage across this will be higher. So, voltage across this higher means as per KVL, this is fixed, VCC is fixed. So, this voltage increases means this voltage will come down, and so that is why this voltage is coming down, but it will have some higher value. This may be in millivolt or microvolt, this may be in volts. So, we are getting an amplification, but with a 180-degree phase shift. So, that is about the working of the amplifier. So, we can stop the class of now. We can see about another topic in the tomorrow class. Okay, thank you.